Welcome to our AI at AU seminar today. It's AI Pick Two Fast, Cheaper, Good. We have Dr. Chad Jenkins. He's professor of robotics, professor of computer science and engineering. I'm at Michigan, at the University of Michigan. I'm so glad to have Dr. Jenkins here today. He's going to talk about remind us not to overestimate the capabilities of AI as it can lead to unintended or harmful consequences. So let's give Dr. Jenkins one more time a round of applause. Thank you for coming today.
All right, thank you so much, and thanks for having me. Thanks for for your patience while I get set up here. And I have there's so much I want to talk about regarding artificial intelligence and robotics. It's such an amazing time to be in this space, especially with the rise of humanoid robots and large language models, vision language action models. And so I'm glad that everybody's out to hear this talk. I have more slides than I can I can present, so I'll probably just stop part of the way through. But I just want to motivate why this is an amazing time to be in this space, but also offer some thoughts about why we should be careful and say that there's still a lot of research to be done in just the basic aspects of artificial intelligence. And so that's the why I have the title of our talk right here, that when you're thinking about artificial intelligence, you have to pick two of fast, cheap, or good. So we really right now don't have all three, and so I'd like to talk a little bit about that. All right, I think the clicker's working now. Um, and so when we think about whether something is fast, cheap, or good, am I one slide ahead? Here we go. No, here we go. When we're thinking, sorry about that, I'm just getting my stuff set up here. But when we think about where AI is, you think about the Venn diagram of solutions that are fast, cheap, and good, and really what we want is that thing in the middle. But we should ask, where is AI today? Where does it fit in this sort of diagram? What do we need for AI tomorrow? And more importantly, how do we as students and as scholars, how do we prepare for an AI-driven world? How do we prepare you for what's going to look like when we have automated systems that can do a lot of work for us that right now we still do by hand? I originally gave this lecture at the William T. Patton Foundation at Indiana University. And one thing that I really appreciated about having that lecture is they talked about how the American system of education, and the funding that goes into it really has made the United States one of the most outstanding nations of the world, made us a beacon for education and innovation. And everything that I'm talking about is founded upon the investments made in artificial intelligence and robotics and the whole scientific and scholarly ecosystem. And we really need that to continue if we want to be able to have this great system of science and technology that we've been able to create. And I've been a huge beneficiary of that. So this is just some of the robots that I've worked with. And so at the bottom is the PR2 robot. That was one of the first mobile manipulation robots. I bought one of those in 2011. And we've seen just such a rise in those robots. When I came to Michigan in 2015, one of my first purchases were the fetch robots in the middle. These were robots that could move around. They had arms to pick up stuff. They had eyes to basically see their environments. And now being able to have humanoid robots, we have those right here in our building, and we're just seeing more and more great humanoid robots come up. Look, we're just seeing just a rapid advancement of the technology that's founded upon decades of research and investment. And this is just showing some examples of what we've been able to do. So one of the things that we want to have robots do is just be able to pick up stuff in cluttered environments. So, my kids basically have, if I go to my house, my kids keep the house a mess. And how does the robot deal with that, with all the occlusions the unstructured nature of these types of environments, to be able to see things, interact with them, pick them up, do the types of things that we want robots to do in our common human environments, and do those robustly. And we're making rapid advancements to that towards doing that. But just as important as the technology that we develop, it's also the people. What we develop as higher education is we're really about people and ideas. We basically, we educate people about the ideas of our disciplines, and we show people how to extend those in new ways to create this ecosystem of being able to have innovation at sort of that has just grown and provided such a benefit to society. Um, I think I'm obligated by the Big Ten to just also talk about, like one thing that's great about it is just being able to win a national championship. This is something that I love about being at a big school is that, people go around, they see the big block M, and they're like, oh wow, and they want to talk about football and all these things. And that's a way for me to start talking also about the things that we do in engineering and build connections across universities like we do at Howard University. This is just I'm just showing. I would wear this thing when Michigan was in the college football playoff. We had a postseason chain. I had a little little thing with my colleagues from UT Austin. We may have seen them in the playoffs, right? And these are amazing roboticists. Peter Stone, Louis Sentis, who are amazing people in AI and robotics, and just meeting these people. And this was me in Texas with my postseason chain on. And then my daughter went to Switzerland with me. We watched the game in Switzerland with the championship chain. And so I just got to meet all sorts of great people. This is Christy Morganson and Veronica Santos, who I actually developed a lot of these ideas with. These aren't just research ideas. These are relationships that we build up. And we don't just help each other, we help lots of people come into our discipline that just really makes the AI and robotics ecosystem go. And one thing that we came up with when I was talking to Christy and Veronica was that, that they had mentioned that I think one of them, Christy or Veronica, had said, when we're thinking about AI, it's a lot like Francis Ford Coppola when he was making The Godfather. The studio was pushing him to make this movie, this classic movie, and try to do it, as fast as possible. And Francis Ford Coppola said, well, he told the studio executives, you can think about, if you want a movie, you can make it fast, cheap, or good, and you have to pick two of those, but you can't do all three, right? And that was an apt analogy that we've now used to start to think about the performance of artificial intelligence in its direction. The only thing that's different, and this is for people of my generation, is that it wasn't necessarily the Godfather that we were talking about. It was actually Smokey and the Bandit. And so Hal Needham, told the studio executives, that when there's making Studio and the Bandit, you can get fast, cheap, or good, but two of those, but not all three. Um, Classic movie that stands the test of time. Anyway, but going into this analogy a little bit more, if you think about, picking two of these, let's say that you wanted fast and good, right? You could try to get people to do that, right? If you can get a large number of people and you get them to do things really fast, you can get something that's pretty good and it could get delivered in a reasonable amount of time. But that means that people are more expensive. It costs a lot. People are expensive to be able to. Human effort is really it really costs a lot of money to make that happen. Um, and so, so I would sort of label that what we have as sort of, if we pick those two, that they're more expensive. If you think about the AI of the past, or the AI we still use, but it's sort of like the traditional AI, sort of like what we have for Google Maps. Google Maps, you can plan a route. It's doing essentially search on a graph structure, and it works really well. I have a lot of confidence in Google Maps and the search algorithms. And so they can be done cheaply. We can use modern distributed systems, and we can distribute that search and we can maintain large graphs. And that can be cheap and it can be good, but it's not always fast. We're limited to very structured projects that will take time to deliver. So, it has to search through all possible options to find an optimal solution. And so that's really what we have here. And when people think about the current AI, such as like a Chat GPT, they think of that as like, well, that's the best of all worlds, right? That's going to be fast, cheap, and good. Um, and it just works. That's what we see from a lot of people. Current AI just works. And so if you just want to say in the chat really quickly, just to get to this point, does anybody know what this is? Can anybody tell me what that is? You can put it in the chat, or you can just unmute and say it. Does anybody know what what we have here? Any guesses on what that is? A barrier? Salmon. All right, salmon's good. Yeah, salmon. Um, if you think of this as sort of a prompt for image for an image generation for a diffusion model that generates images, what prompt do you think generated this? There we go. Salmon going upstream. I like that one. Yeah. So actually, this was one a student sent me that I thought was pretty good. It's basically a salmon swimming down a river, right? And so I mean, that's not wrong. That is a salmon swimming down a river, but I don't think that's really physically plausible. I don't think you can have like a fillet of salmon swimming down a river. And so really, we have to be mindful about how we use artificial intelligence. So I would make the argument that even if your artificial intelligence system is right 99% of the time, do we know, can we characterize the 1% of the time when it's wrong? Because if we can't, then then that really makes it, then how can we trust any of the results? And I'm gonna sort of go into this a little bit more, but I will say one thing that one incident that sort of strikes home for me is it happened on my birthday, my 46th birthday, January 9th, 2020, when Robert Williams was wrongfully accused of theft by an artificial intelligence system. There was a robbery that occurred in Detroit. They essentially took the surveillance footage, ran it through a neural network, and Robert Williams came up, but he wasn't the actual he actually did not commit that crime, and he was arrested in front of his family and his neighbors, really embarrassed, humiliated, and he was held for 30 hours by Detroit police. And so, and he goes through this account in the Washington Post, a really great op-ed in the Washington Post. And it really means that if we have, that if you could just start to use these artificial intelligence systems, um, you have to understand that they're not foolproof. That is not evidence. It's a guess. It's, a guess that may be 99% correct or 90% correct, but you can get lots of false positives. And so one thing that's happened as well is there was research that happened at the time. It was about taking blurry images and then trying to use artificial intelligence to scale them to produce higher resolution images. So they took a blurry image of President Barack Obama, and they tried to upscale it, and they got something that does not look like Barack Obama. It maybe says a little bit about the bias that's in the network. Maybe the system didn't, have is biased towards certain faces. Maybe the data set wasn't really collected as well enough or as thoroughly enough as needed, and so you get mistaken results that are at issue. And so our current AI doesn't just work. It's not just it just works and it's amazing. But really that's the dream AI that we're thinking of. Like it just works. We can rely on the results. They're solid. And that's sort of, at the middle. That's what we're going for. That's the dream. But what the current AI is actually that's really not the best quality, right? So when I originally made these slides, I made these slides back with Christy and Veronica back in 2019. People hadn't seen, we'd seen it in the artificial intelligence labs and the robotics labs, what AI can do. And now people can go through and they can look at the results they get from a chat GPT system or a diffusion model for images or other types of LLMs or vision models. And they can see that, like you get something that's pretty good, but is not necessarily as good as like maybe having a person who is really good at what they do produce that result. So we get not necessarily the best quality. We get something good, but not always great. And so this is really what the landscape looks like right now. And so I want to just put an example for this for you to think about. And so imagine you have to fly from Seattle to DC, right? And you've got two choices to think about. So let's say on one hand, like you have, if I just looked it up on, if I just took the current options that I have right now, I could get a ticket from Seattle to DC for about, that's going to take about, 5 hours, cost about maybe $400. And so if I have, and so this is going to be powered by a human crew, people who are making a lot of things happen. So, maybe 500, let's say $500 ticket, 10 hours door to door to get from out of my house through traffic, through the airport, situated on the flight, then out to, then the flight happens and I land and I'm doing my thing in DC. And, maybe it's like my on-time departure rate is about 85% that it actually happens on schedule. And so that's with our human crew who's doing things, who's doing all sorts of things to make this happen, from pilots to flight crew to maintenance, air traffic control, TSA, gate agents, and lots of other people that you may not see in the background. Um, but but let's say I could automate all of that with an AI crew. Like I can just have artificial intelligence do all of that. Well, maybe I could get costs down. Maybe I could do it for $50 in ticket. It could be 6 hours door to door because now they can optimize some sort of route, or I don't have to. I can automate the security process, and maybe it's gonna, because it's all sort of automated and work. I can improve the on-time departure rate. And so the AI crew sounds pretty attractive, cheaper, more efficient, faster. But then you have to ask the question, because whenever you get on a flight, you're taking your life in your hands, right? And so which flight would you take? Right? It's a question. I'll let you think about that. You don't have to put in the chat, but if you wanted to, you could say which one sounds more attractive. But before you do that, I would say, well, what happens if I now told you that that you had, that your chance of failure, that there is an incident that happens, is sort of with the human crew. I think we look at like the transportation guidelines. I think there's a failure every 1 in 100 million flights that happens. And I think that the number is actually better than that, but I'll say 1 in 100 million, right? And so if we think about that in terms of the number of nines, like the percentage, it's 99.9999999% success rate. And that's why we take these flights, because we have a lot of confidence in the airline system. But let's say for my AI crew, that now it's you have the chance of a 1 in 1 million failure, right? And so now I'm down to 6 nines in terms of my success rate. Which one would you take, right? Given that you could have a possible failure. Um, but now if I took that and I said, well, it's not just that, that's maybe not, maybe if I look at that success rate and I thought about it a little bit, matched it to what artificial intelligence sort of does right now. That success rate is actually more like 98%. Maybe we're getting up to a little bit higher, but now if you had a 2 in 100 chance that there's going to be a failure and an incident on a flight, which one would you take, right? Which one would you put which one would you sort of trust with your life? Not just your life, well, I would say if I'm shipping goods, I would say, like I'm shipping socks or a USB charger, or like just get goods I'm getting from an online retailer. Maybe I'm good enough with maybe 2 in 100 failures is good enough. It's not hard to reship that. These are just material goods. But if it's something that really matters, like if I'm flying with my kids, or we're shipping an organ, or we're trying to deliver things that people need to survive, which flights would we trust at that point? And so it's not necessarily to say that AI is bad, like, but it gives us a certain level of capability that we have to modulate when we're thinking about, what we're in terms of actually delivering proper decisions or proper automation. And so at the time, if we looked at it, these 2 in 100 failures can be made worse. So there's lots of research into how we think about, in terms of potential vulnerabilities in neural networks. So in this case, back in 2018, you could take an image of a panda that would be recognized as a panda, add some random noise to it, and it would be then recognized as a gibbon very confidently by the neural network. And so that's that's something that you have to think about, where we're going out of distribution of the of what the neural network has seen. And so there's all sorts of other issues, such as putting stickers on a stop sign so it's recognized, instead of being a stop sign, it's recognized as being a speed limit sign. Being able to have a turtle be classified as a rifle, handwritten digit recognitions. There's all sorts of things where these systems are not necessarily perfect. They're where they can be vulnerable. And so this is something for you to consider, that what we have now is that we have, what we know now as people who work in artificial intelligence is that AI needs to be demystified. It has many incredible uses. It's really beneficial. There's so much that we can do about new possibilities that are unlocked, but we have to think about how we're going to use that the right way as it gets out into the world. And then on the horizon is that we want to be able to have people match the type of risks to the type of tasks that they were going to do for artificial intelligence. As we improve it, as we improve artificial intelligence, it gets better and better and better. There'll be more types of tasks that we can use artificial intelligence for, but we always have to know that there's going to be risks involved. And in the long-term future, if you want to hear, I don't know if I'll have time to talk about it in this talk, but I also would say that digital computing is not necessarily the best match for artificial intelligence. We spend a lot of our time in AI when we're running a model, flipping bits from 0 to 1 or transferring bits over a wire. And GPUs have essentially made artificial intelligence better and more tractable. And there's all types of and it's really sort of revitalized a lot of computer architecture to think about the new problems for artificial intelligence. But maybe there's other opportunities besides digital computing that would be a good match for AI. And hopefully I'll get to that, but I would just put that thought out there. um there we go. There we go. All right. So I would and by the way, thanks for the comments in the chat. I appreciate that. Human crew still sounds good for right now. And so if you're not familiar with artificial intelligence, really when people say AI, when they say artificial intelligence, these days what they mean are deep neural networks. And so what these networks are really doing if you just go back to high school algebra, they're estimating a mathematical function that we take some input X, we run it through a function F, and we get an output Y. And so that really is a lot of what we're doing for neural networks. And so just to give an example, let's say I wanted to estimate the potential restaurant quality, and do that from the number of stars it has on Yelp, right? And so Yelp, if I'm trying to figure out something to eat, I might go to Yelp. Do I trust what they're saying, or do I not trust what they're saying? Well, what I could do is, if I wanted to, I could get some examples of this. Let's say Capital Grill is one example, and Smash Burger is another example. And if I tried those, and I sort of matched those to the quality of restaurant and my view of the quality of the restaurant, I could get a lot of data from all sorts of restaurants that are around. And what the neural networks are doing, or any type of supervised learning algorithm, is trying to estimate the function that goes in between them, your trained model that goes in. They can tell you that it can essentially gives you this ability to now predict. So if I get some new restaurant, let's say Thai cuisine, I can now take that restaurant, and I can take the number of Yelp stars that it's given, and then predict the quality of that restaurant for that how much I would like that from my personal taste. And so this model really gives us a lot of predictive power, whether it's from a neural network or not, but usually we're using neural networks to do this now. If we wanted to then scale this up, in terms of being able to do recognition from images, you wanted to be able to detect people in various images. Such as being able to do things, it's actually pretty easy these days to collect a lot of data about surveillance of people. So you can do facial recognition, you could recognize cars and buses, boats that are happening, people who might be, engaged in activities, some good activities, or maybe we can classify, the bad activities that we have. We can use those same types of systems to do this types of recognition, except that now instead of just having one input dimension as Yelp stars, we have many more dimensions because every pixel now becomes a dimension. And for that, we need much more data to model this function. So what we have, so if we have an image and a label that's coming out, so we want to be able to predict like what type of thing that we're seeing in an image or what type of activity. We'll collect a lot of training data, examples of all possible labels. Let's skip that slide. And then basically we can go through and update our model using typically now stochastic gradient descent type algorithms to essentially update the training on these models, and then be able to predict, given some new image, we can have predicted recognitions of things that we might see. So for in this case, we're trying to predict where cars are and where people are if we want to be able to look at the flows of traffic. But there's issues with this, and that oftentimes we see the positives of this. We see the cars, we see the people, we see the positive recognitions, but we can also sometimes miss the things that are false positives, things that are recognized but recognized incorrectly. But we also have a lot of false negatives all over the place, that are things that should have been recognized that were not recognized. And so this starts to become a big issue, because if they weren't recognized, how can we say that they were supposed to be recognized and understand those mistakes? And so what we a lot of times do in artificial intelligence is we try to figure out, how did these mistakes occur? Do we need to fix this by collecting more data and retraining? Is this something that we could do to maybe have other types of artificial intelligence systems like Bayesian inference, or let's say kernel methods or a search algorithm, be able to come through and fix some of these mistakes? But from an impact perspective, if a decision is being made on these types of artificial intelligence outputs, there's a cost to be made. That cost could be somebody not arriving to their destination in a timely manner. It could be more harmful than that, such as an injury or a fatality. And so those are things that we have to think about as we're developing this technology. And so that's why I would suggest that people match the type of risk to the type of AI. And that's what I'll sort of talk about next. And then if we think about AI for doing autonomy, for creating more automated systems, and then also being able to do data analytics for us, crunch on data for us, then there are a growing number of risks and consequences as we scale this out to more and more important tasks. So, for instance, if you're thinking about consumer shipping, that's sort of a two nines of reliability. That's a perfect thing for us to be thinking about. Those types of logistical things, and those types of logistical tasks, and that's where we're seeing a lot of movement right now in sort of the sort of space for artificial intelligence and robotics. When we start to think about autonomous driving, which where you need sort of five nines of reliability, right? Imagine what it would take to insure an artificial intelligence system. If you're a automobile insurer, would you take a risk on an automated system? And so if you think about low speed autonomous driving, that's getting to the point that you would be able to insure it, or would be, at or better than a person in terms of the risk that it posed, that's going to be five nines or nines of reliability. If you think about what it takes to rival commercial airlines, right, where you have skilled people, then that's really, that's another level. And I don't know, and artificial intelligence as deep learning may be able to get there at some point, but that's still a long ways away. And if you think about really critical tasks, such as maintaining the nuclear stockpile across the world, right, where it cannot fail, right? If it fails, then that's a massive consequence. All you have to do is watch the Chernobyl documentary, or a lot of roboticists are motivated by what happened at Fukushima in Japan. just about a decade ago. Those failures cannot happen. And so what does it mean to have 12 nines of reliability? In addition, we know that, as we're finishing up our semester here at the University of Michigan, we know that, and there's lots of students who are training artificial intelligent systems, training neural networks. We're making those types of systems more energy efficient through computer architecture and smarter algorithms, but it still costs a lot of still a lot of energy goes into training these models, and so we have to think about not just improving the efficiencies of these algorithms, but how they're going to be how it's going to be impacted impacted on our environment, our sustainability. Where's that energy going to come from? And so those are many things that we have to consider. And so one thing that I would say is that, and I think I'll have time to really talk about this, is that if we think about just the current AI as maybe not being the most energy efficient or not the best quality, there still is that dream AI in the future that can provide this level of greater levels of reliability and better cost for efficiency if we wanted to think about what that could look like. And so for this, I think we have, there's people out there with ideas about how to do this, and also other ideas in our scientific ecosystem. And in order to realize that dream AI, I would make the argument that you have to have continued and significant investment from the federal government, similar to what we had over the last century. I would highly recommend for anybody who's interested in how we got to this point in artificial intelligence and what it took for us to get here. I would highly recommend the Quest for Artificial Intelligence. That was written, I think it came out about 2009, before the big neural network push, by Nils Nilsson, who is a pillar, a pioneer in artificial intelligence. A-star planning, if you know A-star planning, Nilsson and many of his colleagues were responsible for that enabled us to have Google Maps and things like that. Because we don't know where these good ideas are going to come from. We didn't necessarily know that artificial intelligence was going to provide returns like it is now. And so we have to let a thousand flowers sort of bloom. And so if we go back to what Nilsson to what Nilsson chronicles in artificial intelligence, the artificial intelligence that we think of now really dates back to almost a decade, I mean, almost a century ago. Some investments made by the federal government outside of after World War One, those investments leading up to the rise of computing for doing things like creating in Los Alamos to create the nuclear bomb, but also to do control of artillery. But those things that really supercharged the computing revolution. And so Norbert Wiener talks about that in the 1940s. And then after World War II, you saw, sort of new ideas come about, and sort of that was at the foundation of personal computing, maybe moving away from mostly being in defense to thinking about, broader applications across society. And so the artificial intelligence that we think of now, really was sort of, or just the term artificial intelligence came about in 1956 with the Dartmouth Conference. And soon after the Dartmouth Conference, that brought us a lot of search algorithms and the AI that's powered us to thus far. It also, just a few years after that, came the first neural networks from Rosenblatt. And so these ideas that we're talking about now have been around for at least a half a century. But it took time and investment for that to really catch on. And so we think of this as sort of like the evolution of AI, right? There was sort of the first wave of handcrafted knowledge, and search algorithms, and that really came about in the 1980s and 1990s, and helped us build autonomous cars. the robots that we've seen, original speech recognition systems. And then neural networks, the machine learning part was the second wave that had a big boom it came about in the 70s and 60s and then sort of went away, had an AI winter. Then it came back in the 90s and then went down for a little bit. And now since 2010 has been on a huge upswing. And but then there's a sort of third wave that's underneath that we really have to think about. Um, if you want to know more about how this plays out, I would highly recommend looking at the tire tracks. That sort of talks about how federal investment in various areas of research have grown into $2 billion, 10 billion-dollar markets, and this was 2016. That's grown since then. I highly recommend one thing that I would note is as I was a part of the tire tracks for 2020 for the 2020 version, and I remember Alex Weibel, who's a developer who worked with Jeffrey Hinton to develop modern deep learning, and they were labeled as neural nuts at the time. People didn't think these ideas were going to work, and basically had to attract funding from outside the United States in order to make these ideas that are now just commonplace in artificial intelligence in our universities and industry. And you can't, and it's just all over the place. These were ideas that nobody thought would work, and there were some people that made it that had to really be committed to it and found diversity. Fortunately, there was diversity across the world in terms of funding that they were able to try these ideas and help them mature to the point that they could show what it could do. And it turns out it was a huge boon for both the nation and the world. Um, and so that evolution is really, really sort of coming about. I'm going to skip some of these real quick. Just sort of talking about first wave AI. Um, this is really, if you think about its evolution from the founding fathers, this was, it went and did very simple games all the way to beating the chess grandmaster in the 90s to now basically doing city scale mapping and for self-driving cars and doing online routing. I will just show this video because I just think it's really cool. This is something my colleagues Ed Olson and Ryan Eustace produced. This was back in 2013, 2014. You can build fabulous models of space and I mean of city environments from a car. And so you're seeing in blue here what the robot has built up over time, and then in red what the robot sees from its laser range finding at the current moment. And so our robots, from using sort of that first wave of artificial intelligence, we can you can get really good models of geometry of the world. Where the problem is that we don't necessarily understand the semantics of this space. We don't know. This is just a collection. What we're seeing is just a collection of points to a computer, but it doesn't understand that there's a bicyclist riding through the middle of the intersection. That certain points belong to a car or a tree or the road. And so that understanding those semantics is really a big part of what has been part of the second wave of artificial intelligence, and that's being able to learn from lots of data. And so for these things that require much more subjectivity, we've seen deep learning be able to help with this. And so deep learning has been able to spot pedestrians, do the facial recognition that we've seen, and it can do it pretty well. And but it's at that sort of 99% level, and that's being able to learn from lots of data. We've seen this, if you've used Stable Diffusion, such as DALL-E, or you've used Copilot, now ChatGPT, you've seen the benefits of being able to learn from lots of data. And the images that we get from a Stable Diffusion system are just incredible. They look realistic, even though they're not. And I'm just showing ChatGPT right here. For robotics, we're actually seeing these models being used for humanoid robots. So you can generate lots of data in simulation and then be able to try to apply that to your real robot to have it walk and perform various dexterous activities in a wide variety of environments. But even this required lots of investment. So if you go back to Rosenblatt's perceptron, which was one of the first neural networks to really be out there in 1958, it took about 30 years for that to turn into the speech recognition that became the foundation for things like the Amazon Alexa. And those models were proposed in 1989, but then really took off in the during the 2000s and catalyzed in 2011 by AlexNet. As we've talked about before, these systems still have issues in terms of being, they can learn from lots of data, but they can also, things that are outside of that data set can be a problem. And so what you're seeing is in this third wave is being able to combine the first and second wave of artificial intelligence to generate explanations. So for instance, if I have a handwritten character, like somebody shows me a handwritten character that looks like what we have here in the black, the question is that a 9 or a 4? And and if I look at it, it could look like either. Both a 9 and a 4 are a good guess. But I would like, but if I think it's a 9, I should explain why. I want an AI that's going to explain why it thinks it's a 9. Or if it's a 4, we want an AI that can explain why it thinks it's a 4, and not just sort of, assume that the system will be a black box. And so, one approach to doing this is to use the training data to generate a model that can generate possibilities. And then from those possibilities, you can use a model-based system, something that has a logic to it, or a known model, to be able to then explain what came out of the system and have that be your your final decision. And there's many different ways that you could think of that. That's just sort of what came to my mind, and we have papers that sort of address things this way, but address the problem this way. But really, like that's really one of the next big challenges that we face. How do we get the speed and recall power of neural networks and combine that with the reliability and explainability of our modern or traditional AI based systems? And so that's really on that third wave. I teach a class, Robotics 102, that really is an introductory programming class that introduces students to how we do search, and we build them up to do an A-star planner in their first year on campus, in their first semester on campus. And then they do a small multi-layer perceptron, excuse me, to then start to think about how they can do data-driven neural network-based AI. And then we have follow-on classes that are available at the sophomore and junior level and build up to senior level classes they're at the state of the art in artificial intelligence. And then, as I said before, this third wave is I think where there's uncharted areas that we need to be able to get reliability and fast recall power. And so Cheryl, I'm assuming I have about maybe 7 minutes left, so I'll try to talk about this really fast.
That's correct.
What's that?
Oh yeah, that's a good amount of time. We have
That's
it about 7 to 10 minutes.
7 to 10 minutes. All right. Um, And so one thing the last thing I'll talk about is how do we train students for an AI enabled future? And I believe that one thing that you have to be able to do is rethink the disciplines that we have. As somebody who was trained as a computer scientist and started in computer science in the early 90s, there were people that could understand all of computer science, single individuals, that had the whole view of computer science. And now, 30 plus years later, that's impossible. No one person can keep all of this, or not even one small group understands everything that's happening in computing. And that's suggesting that we have new disciplines that are emerging, such as artificial intelligence. And one thing that we've been able to do here at the University of Michigan is create a robotics major, thinking about robotics as its own discipline so we can use to prepare students. And so Robotics 102 is part of that. One thing that we've did as part of this is we've built a very low cost robot platform. So this is the MBot. The MBot, this is the OmniDrive version of it. It can do all of the mapping that you would do for on a big on an autonomous vehicle. So the laser range finding, we introduce students in their first year to how they can build maps with this platform, how they control it to do path planning. And how it can be used to do autonomous control. And we've built on this to have classes in robot operating systems at the junior and senior level. I mean, junior and sophomore level. We've built on this to be able to have classes and that go into simultaneous localization and mapping, the mechatronics of how we build these types of robots. And we've been able to, we launched this program back in 2022. Now it's I think we have over 200 majors in the program. And really it's, you know, it's growing these disciplines because we have to, because in order to keep this system of eco innovation going, we have to train students earlier, take these classes that may have been at the graduate level or upper levels, and then be able to have them available, train students as undergraduates how to think about AI and robotics and automation in their in that's going to just be a part of their world, and have a workforce that's going to go into research and development, industry, even the public sector, to think about how this type of to develop this technology and also extend it in new ways. Coming back to the patent lecture and talking about that education is really one of the most is if not the most outstanding asset of the United States, of our American system of it of our American economy and structure. Like really, this is, education is one thing we do that has been just a standout exception, that has uplifted so many people around the world, and that is really important for us to have a viable society moving forward. And so that's why I've taken a big step to create I led the creation of our Michigan robotics major here, our undergraduate major in robotics here. If you want to, you can read about it online at robotics.umich.edu. A lot of it gives a big shout out to Joanna Milinchuk, who was our associate dean, who helped us lead through that. And so I'll skip that slide. Um, if you want to read about it, you can read about it. We have a paper online about the design of our program on Archive. So if you're thinking about doing a major in robotics or AI or even a minor, we went through the design of our major, all the things that we had to do to really think through what it makes to be in this one of these leading cutting edge undergraduate programs. And really, the last thing that I'll leave you with is that this is part of a larger effort to essentially develop more wider pathways, for enabling students to be successful, have career-long participation in robotics and AI. And so that's, what we're doing is what we can do in our undergraduate and graduate programs, because that's what we know how to do, but it has to connect back to K through 12 education, working with partners to do that. And I can tell you the number one question that students and parents had for me as we were creating a robotics major is basically, what job can a student get from with a robotics major? And so we have to work with industry. We need partners in industry to help us enable students to be successful and to have a thriving innovation ecosystem. And with that, I'll just have a pointer to a to a to an article that we have about our distributed teaching collaborative model for working with other schools to do open source collaborative development. That's a great complement to what we've done here at Michigan for our robotics major. With that, I will stop just before 10 to the hour. Thank you very, very much for listening. I'd be happy to take any questions that you have.
Okay, so let's give him a hand. Thank you so much. Do we have any? I have a couple of questions, but for those in the audience, or any questions in our audience, you can put them in the chat if you have questions. If not, I have a few. Well, while they're thinking of questions, I had a couple of questions about the robotics program. Now, in the archive article, I saw about 9 collaborators. Are all of those guys teaching or doing outreach, or what are they doing with the program?
Right, right. So I will go back a few slides, and so if you look at all the people who were there, all of these were people at Michigan. And
Right.
so
Mhm.
so I was the associate director of the Michigan Robotics Institute, who led the creation of the major. Jesse Grizzle was the director of the Robotics Institute. Ella Atkins led the graduate program and really helped us make that go. Leah Sternley is now the associate chair who's leading the undergraduate program, but she was on our undergraduate committee and teaches a class on human robot systems. Um, and so like, so basically thinking about like how we build in teamwork and professional communication into the sophomore year of our robotics program. Elliot Rouse was created our mechatronics class, and that's been very popular. You build a ball bot like on Star Wars. They have that ball bot in Star Wars. You build one of those in his class, and he goes through all the sort of manufacturing and parts of that. Mark Gusdile is faculty in computer science, and he basically gave us a lot of ideas. And so one idea that he gave us was to instead of trying to lead with one particular class, he gave us the idea of having three classes for sense, plan, and act. So robots sense the world, they plan towards a goal, and then they take actions. And sort of instead of putting one of those first, we make all three of those classes available in our first year to students. And if a student takes all three of those classes in their first semester, they've done the robotics super semester. And then Damon Provost was our managing director, and Kimberly Mann is our unit administrator, who did a lot of the heavy lifting to get the administrative aspects in place. And Joanna was the associate dean who helped us make this happen under Alec Gallimore, who was our dean of engineering, who really gave us Alec is now the provost at Duke, and Joanna is the dean of engineering of computing, informatics, and engineering at Indiana University. But they gave us the room and the foundation to build this program, which has been pretty successful.
And another quick question, with the MBot, what type of, do you know what type of processor that is? And is it something that other institutions can get a MBot?
Absolutely. So I think so one thing about the MBot is the bill of materials for that MBot is about $360, right? I can't, some of those parts are imported, so I don't know what that's gonna be in the future, but the highest priced cost on that, the highest priced item is the RP LiDAR, the spinning laser rangefinder, and that's
Yes.
about $100. It runs on a Raspberry Pi, so so you need a higher end Raspberry Pi, but that's
Like,
gonna depending on and there's also like another board that we have on as well. There's a little bit of a custom board that we have to provide the specs for, but but those materials come out about like $90, for the compute, and then everything else can be laser cut plastic, some servo motors, the wheels, all of that comes out, so the robot is about $360 each. We'd love to be able to mass produce them and make them more available. We have to, but but we can work with individual schools to get them up and running with the MBOT if they want to be able to do it. And we've got courses available that people can work with, if they wanted to be able to take those materials and then be able to use them. So the idea is that we do open source course development. So what we develop for our courses, we work with other schools to be able to develop the course materials, and then we open source it so that everybody can use it and contribute back. And so we're trying to make it such that anybody can pick up this platform, and anybody can pick up our course materials and be able to offer the classes.
that
This
is
yeah, this class is offered as a 300 level class at Howard University and a 300 level class at Morehouse College in Atlanta, and then as a 200 level class at Berea College in Kentucky. And we are in discussion with other universities, faculty at other universities to be able to offer this course.
Oh, and I see another question in the chat. But a quick question for the Sense Plan and Act courses, are they like a 1 hour or a 3 hour course?
So if you go to, I'm going to put it in the chat, hellorob.org, you can see our course materials.
Thank you.
Um, And so, so basically it's actually a 4 hour course because it's lecture and lab, at Michigan. And so we do it flip classroom typically. So students watch videos of me lecturing and, and I know that that's not awesome watching those videos, but when they come to class, if they watch the videos, they get to hack on robots and we get to use that time productively. So it's not like boring flip classroom where you hear somebody, talking about equations and then you come into class and you do more equations, right? You actually get something working and we sort of use that. We try to get as much lab time as possible. Um, but it can be modulated. I think at Howard it's a 3 credit course. But yeah, it's really we don't impose a particular structure. People can pull from it what they want and offer it as the class that they want it to be.
Mm. Oh, and then there's a question in the chat. It says, do you think that eventually untethered robots will have onboard computational power at a similar or higher level than current foundational models, like OpenAI?
I think that's it's hard to say. Um, I I I think if you look in the near term, I think what you're seeing from NVIDIA, like once you train the model offline, or okay, let me channel the NVIDIA perspective, right? So I've been able to hear what the NVIDIA approach, and here well maybe I'll just keep this going, but NVIDIA sort of says there's going to be you're going to have three things, right? You're going to have an omniverse to do simulation, and you're going to train your models and doing all sorts of simulation and maybe a little bit of real world data. And then you're going to have a big AI computer that's going to train up a model. And then once you have that model, you'll be able to take it and apply it onto your robotic systems. And the onboard compute for those onboard systems are going to get better and better and better, fast enough that you could deploy one of those foundational models, potentially onto your robot. And I think that's the vision that many people have. Um, I would make the argument what I see is a little bit different than that, although those advancements are needed for us to have great AI enabled robots. I think what you're going to see is, in order to have the right reliability we need, I believe that Bayesian inference, my particular viewpoint, will be used with these types of methods where let's say you get a guess from a foundational model of solution to a problem, and then that you could use that solution directly, but you would also sort of in parallel run it through a search algorithm or a Bayesian inference system that would give you more reliability, maybe give you a better sense of the probability distributions, or be able to verify that solution or propose other solutions that can be verified. And what that looks like to get that level of reliability, I'm not sure what the compute's going to look like. But also another perspective I would take is that, if I go through the digital compute, if I take the digital computing route, it may be the case that is going to be too inefficient on its own. And there's work going on in sort of analog hardware-based approaches to doing neural networks that could be better and potentially give you much better distributions. And so so analog computing, I think has potential for making a comeback.
So any other questions? I probably have a whole bunch, but I'm going to be good because I asked a lot already. And so, well, let's give Dr. Jenkins one more hand. Y'all can give him a virtual hand or thumbs up. And let me stop. I think that's all for our recording for today.